All right, so we're going to take a quick second to review op-amp circuits. We know that the two golden rules of op-amps from EE220 when we learned them are these right here. The first one saying, so let me just draw like a rough sketch of an op-amp circuit. We have like our, from DC at least, we had our input source, say here. And then we have our op-amp here. This is a inverting topology. So this would be my circuit. And so the first golden rule is that the plus and minus terminals are always at the same potential. That's this terminal here and this terminal here. So right here and right here, the voltage are always the same. That's the first golden rule of op-amp circuits, and basically the first tool we have to help us solve these kinds of circuits. The second rule is that no current will flow into the op-amp terminals, okay, the input terminals. So we have an input terminal here and an input terminal here. We just said that the first rule was that those two terminals are always at the same potential. So if the voltage here is 0, then the voltage here has to be 0 as well. The second rule says that no current flows into these terminals. So if I were to zoom in here and just write this current here, I, is equal to 0, and this current here, I, is also equal to 0. I guess we could call one of them I minus and other one I plus, but it doesn't matter. They're both 0. So what that means for the solution of our op-amp circuits is that whatever current flows here, it comes to this node, and when we see KCL, we know that if no current flows here, that means all the current has to flow here. So that makes solving these circuits pretty easy, because we can just set the current through this resistor equal to the current through this resistor and then solve, especially when we just have ground on the plus terminal, because that makes it even easier when this voltage is 0. It makes some of the terms go away. But those are the two golden rules of op-amps, and so if we had, all we have to do to analyze these in terms of, AC circuits is we don't have a DC source anymore. We're going to have an AC source. And so in a circuit like this, all I would do is I would get rid of my DC source and I would replace it with, say, an AC source. Okay? So let's just say I call this R1 and I call this R2. This will be V out of T, and this would be my V in of T, right? And so I can just call this node right here V in, and I'll call this, actually I don't necessarily need to label all the nodes, but I guess I could, but let me do it in a different color. I'll do it in gray. I'll call this node V in. I'll call, this is my V minus node, this is my V plus node, and then this is my V out node. Okay? And the signal at V out is this, V out of T signal, okay? So that's just me labeling my nodes. So if I wanted to write the expression for this circuit exactly like I just said, I would just take the current through this resistor, IR1 of T, and the current through this resistor, IR2 of T, and I would just equate them, right? IR1 of T is going to be equal to the voltage at V in minus the voltage at V minus divided by R1, right? Which is V in of T, basically. And then I just said, right, that the voltage here is 0 since this is ground. So then, according to rule number 1, the voltage at V minus also has to be 0. So that's just going to be minus 0 divided by R1. All right, that's the first current. And then IR2 of T is equal to, in this case, it's going to be the voltage across this resistor, basically. So V minus minus V out, right? And then divide by R2. So let's go V minus minus V out divided by R2. So that's going to, so we know V minus again is 0. So it's just going to be 0 minus V out divided by R2. So we have our two equations. Let me just grab those and I'll minimize them. Put them over here for now. And then we can just equate those two, right? Because like I said from rule number 2, no current flows into any of the terminals of the op-amp. So IR1 is going to go right through and flow into R2, and that's going to basically mean that the two currents are going to be equal to each other. So I can just set these two equations equal to each other. So I can write V in of t over R1 is equal to minus V out, minus V out of t divided by R2. Oh, I was supposed to write VO of t here too, and I forgot to write it like that. Okay, so V out of t. And so if I wanted to solve this equation for V out of t, all I have to do is rearrange some terms, and I would get that, all I would do is I would get that V out of t is going to be equal to minus R2 over R1 times V in of t, or if I wanted to rearrange this for V out over V in, my transfer function, which we haven't probably talked much about yet, but I could write this in terms of V out over V in is equal to minus R2 over R1, which we saw in DC circuits. This is just the AC equivalent of that same exact principle, that for an inverting amplifier, this is the voltage ratio, or the output over the input, for this particular type of op-amp circuit. Okay, so that's a quick op-amp review. I'll do an op-amp example problem on the next slide, and then we'll be done with module 1. So that's pretty exciting stuff. I'm going to go ahead and end this video right here, and we'll see you in the next video.